I now take the same ruler, but I'm going to make it rotate about the center of mass. So here is now the same ruler. And now I'm going to rotate about the center of mass. Rotation, same direction. I have a stationary axis in 26/100, and it's rotating about there. Center of mass. C is my center of mass. Now there is no force on this pin because of the symmetry, which I just explained. So the pin is not pushing on the rod either. So there is no force at all if this is a frictionless object. So if there is no force at all, then the torque relative to any point must be zero. Not only relative to this point, but also relative to this point and relative to this point. Because if the force is zero, then any cross product of R and F is zero. So now you see the special case that I alerted to in equation number 6. Now you have the case that the angular momentum of this rotating object is the same no matter which point you choose. We call that the spin angular momentum. It is an intrinsic property of a spinning object, and it is the same relative to any point that you choose. And if you want to know how large it is, well, the magnitude of the angular momentum I calculated about C, which is the center of mass, is simply equation number 6, is the moment of inertia about that point C, which is the center of mass, times omega about the center of mass. So Cm, center of mass, and C are the same point. What is the moment of inertia of rotation about the center of mass? That is my 1/12 ml squared. So now I have 1/12 ml squared times omega. That is now the intrinsic spin angular momentum, and it is the same for any point that you choose. Even if I choose a point here in space, you can prove that it is still the same angular momentum. Now we're going to look at other applications. There are a huge number of applications, and in the next 4 or 5 lectures we will go through many of them. In some cases you will say, yeah, that's intuitive, that's obvious. In some cases you will say, not so intuitive. And in some cases you will fall off your chair. It is completely bizarre. It is so non-intuitive that you don't even believe it. You won't believe it until I actually show you with a demonstration that that's the way nature works. But that comes later, not today. On assignment number 7, I give you a problem, problem 7-9, in which I have a ruler or a rod on a frictionless horizontal table. And the ruler has a mass L, a mass M, and it has a length L. And here is the center of mass at C. And I hit that ruler, I give it an impulse, perpendicular to the direction of the ruler. Here I give it an impulse. A force acts upon it for a certain amount of time. And let this distance be, I think I call it D in your problem. And it's on a frictionless table. I do this, bang, very short hit. And now the question is, what will this object do? What does your instinct tell you? You will say, well, for sure it will move in this direction. Remember, it's frictionless, so whatever happens after the hit happens forever and ever and ever. It will never stop. So you will all say, well, it's going to move in this direction. That's very vague, but that's true. But how about rotation? Will it rotate? And if it rotates, about which point? Well, you may say, well, maybe where the point of rotation may depend on where I hit it. That would be a reasonable intuition, but it's not true. It must rotate about the center of mass. It cannot rotate about any other point. Suppose it rotated about this point, just for sake of argument. So after the hit, it rotated about this point. That would mean that the center of mass would then do this. And that's not allowed, because the center of mass behaves like a point in which all the mass is concentrated. F equals ma holds for the center of mass. And so after the hit, a single point, because the center of mass can always be considered to be a single point with all the mass in it, that point can never do this. That would be absurd. So from that reasoning alone, you must conclude that the only way that nature can digest that impulse is by giving the center of mass a certain velocity in this direction, which will never change. In addition, it will give it an angular velocity about the center of mass, and if there is no friction, that will never change. So a little later in time, the center of mass will still be on this line, and it may have rotated 1 or 2 or 3 rotations. That depends on how large I is, and that depends on this distance d. But let's assume that it is now like so. And then it is happily rotating with that angular velocity omega c, and continues all the time with that velocity v center of mass. And in that problem, I'm asking you to calculate the velocity of the center of mass and to calculate the angular velocity about the center of mass. Well, I'll help you a little bit, and I hope that pivot will help you a little more. For the center of mass, what must always hold, the center of mass acts like a point source. So it must always hold that F equals m a of the center of mass. That is really one of the major characteristics of the center of mass. So if we look at magnitude, F delta t equals m times a center of mass delta t. The force acts for a certain amount of time, and that's the impulse. But if, before I hit, if this velocity is 0, then a delta t is obviously the velocity of the center of mass afterwards. V equals at, right? And v was 0 to start with. So you see now immediately that I, that is the impulse, equals m times the velocity of the center of mass. And so the velocity of the center of mass equals I divided by m. And so I have solved for you the first part of that problem. And what is remarkable, that it's independent of B, or D, sorry, we call that D. It's completely independent of D. Whether you hit here with the very same impulse or hit there makes no difference. The center of mass behaves like a point source, F equals ma, and the velocity of the center of mass only depends on I and on the mass of the object. The larger I, the larger the velocity, that's of course quite intuitive, and the larger the mass, the lower the velocity. But now comes the hardest part, and I will leave you largely with that hardest part, but give you a few clues. Because now I want you to calculate omega about the center of mass. And now you have to choose an origin, because you're dealing with torques, you're dealing with changing angular momentum, and so you would probably choose C as your origin, and you will say, okay, let's think about what the angular momentum is relative to point C, before the collision, after the collision, if you call it a collision. What is the torque relative to point C? Well, the torque relative to point C, there is here the position vector, R of C. And the torque is R cross F, and this F acts for a certain amount of time. So this certainly is not 0. You can clearly see there is a torque relative to point C. And if there is a torque relative to point C, the angular momentum relative to point C must be changing. Yeah, you bet your life it's changing, because the angular momentum before the hit is 0. But after the hit, the angular momentum is I about the center of mass times omega center of mass. You can see that if it rotates about the center of mass, it has an angular momentum of rotation about the center of mass, which is I omega. Before it was 0, afterwards it's this. So clearly, there must be a torque about the center of mass. And so now, all you would have to do is to somehow relate that change in angular momentum with this distance d and with I. And you will see that if d becomes larger, that indeed the omega of center of mass, the angular velocity about center of mass, will increase. It's very sensitive. That's also intuitive, because if you hit right in the middle, you didn't expect it to rotate at all. You would just expect this object to translate. And so clearly, the velocity of the center of mass is insensitive of where you hit, but the angular velocity around the center of mass is very sensitive, as I will show you shortly. If you hit here, you don't expect any rotation. Some of you may say, I don't like to take C as my origin. I'm going to pick another point as my origin. I'm going to take this point P at my origin, or any other point on this line. Angular momentum must be conserved about that point, because there is no torque relative to that point. Because any position vector from this point to here is in the same direction as the force. So R cross F is 0. So now we have a point, an infinite number of points. All these points here on this line, the torque is 0. So the torque relative to point P is 0. So there is angular momentum, L, relative to point P, is conserved. It is 0 before, and so it's 0 after the hit. Isn't that interesting? And you can solve that problem and find exactly the same answer for the angular velocity about the center of mass by choosing point P. It's just a matter of taste. Most of you would probably pick C, but if you pick point P, the problem may even be a little easier. Both should work, and I will make sure that the solutions to both will appear on the final solutions, so that you will see that it can be done in two different ways.